Hello, and welcome back to our quantum optics series. I'm thrilled to have you here as we continue exploring the fascinating world of quantum mechanics and optics. In our last lecture, we discussed the quantization of electromagnetic waves and its implications. We set the foundation for understanding the quantum description of energy levels. So, today, we take a significant step forward as we dive into the general description of Hamiltonians in quantum optics. Hamiltonians are like the guiding blueprints of a quantum system, governing how energy flows and interactions occurs. We will also explore the interaction Hamiltonian, which is key to understanding how light and matter interact in quantum systems. So Hamiltonians are usually the key components in order to decipher and get the key insights about the quantum system. We can get the energy levels of certain system, and we can also see how the system evolved in time by uh, by building the operators or unitary operators associated with that Hamiltonian. So by the end of this lecture, you will not only understand the role of Hamiltonians, but also see how they connect to exciting phenomena like light matter interaction, which underpins technologies like lasers and quantum sensors. So let's start with a general description of Hamiltonian in quantum optics. In quantum optics, we usually consider a system, and for simplicity, we will here consider only the closed system made up of the two subsystems. And the one system is the two-level atom, and the other system is the electromagnetic wave that is interacting with this two-level atom. So uh, atom field interaction can be described by a Hamiltonian that has three terms. The first term is the system Hamiltonian that is describing the two-level atom, and the field Hamiltonian describes the energy associated with the electromagnetic field, and the interaction term describes the interaction energy of the electromagnetic field and the two-level atoms. So in two-level atoms, there is usually an electron, and we usually see the interaction of the electron with the electric field, uh, and see how the things evolve for due to these interaction. So for the first, we will discuss the interaction Hamiltonian. That was the third term in Hamiltonian. So we consider a charge distribution in a certain volume of space, and we consider a field interacting with these charge distribution. So from electromagnetic theory, we can write the energy associated with the charge density in an external field, and it is just the integral of volume integral of on charge distribution with scalar potential associated with that field. So in order to get the spatial insights of this energy, uh, we can expand the potential term uh, around its point or origin, and we are Taylor expanding the potential term, and we could see that this is just a Taylor expansion in the 3D or three dimension. And we can recognize some terms related to the electric field, and we could see that electric field is just a gradient of scalar potential, and we can put these gradient in form of the vector electric field and the magnitude of electric field. So the equation 3 is modified by this definition, and we can see the introduction of electric field and its magnitude in the second and third term. So further simplifying things, we can consider that electric field is uniform throughout the region, and we could see that this could be assumed that we have uniform charge density, and due to this, we have a non-divergent electric field because there is no source and sink of no source and no sink of the charges, so there is no divergence of electric field. So we could make this assumption and can add this term that is related to the divergence of electric field into our equation 4. So this gives us the nice result in equation 5, and we could recognize many similar things from electromagnetic theory, and we will make use of this and see how the electric field is interacting with the charge distribution. So putting this Taylor expansion of scalar potential that is depending upon the spatial arrangement of the charges into the this Hamiltonian, traction Hamiltonian, and taking integral of the volume charge density over certain volume, we get these terms. And these terms are quite interesting and easy to recognize, as we could see that the first term is just the interaction of the monopole charge with the potential at the point. And the second term is a dipole moment, and the third term is the quadrupole moment. So we put these forms or these recognizable forms in our equation and get this simplified form. As we could see that there are three interaction terms, and we are usually ignore the much higher terms due to their lesser influence on our interaction Hamiltonian. So we could see that the first term is just describing the interaction of charge with the field in the form of the scalar potential. And the second term is the interaction of a dipole moment with the electric field, as the dipole moment is just the two charges separated by with each other, and they are usually oppositely charged signed charges. And due to and field is arising due to their spatial separation, as there is different values of potential at uh, different points of space. And the third term describes the interaction of charge with gradient of electric field, and this term is arising due to the spatial arrangement of charges then the variation of electric field around in different spatial arrangement and its variation. But for simplicity and for most of the cases that are of experimental interest, we usually take the second term in our consideration, as this is the dipole interaction of the electric field, dipole interaction or with the electric field, and it is because that um, it is easy to excite charges than the collection of free or bound charges, and it is due to that collection of charges and free or bound charges uh, give rise to the internal fields and forces between them. So we usually in quantum optics problem usually use this form of the interaction Hamiltonian. So today we explored the general description of Hamiltonian in quantum optics and their significance as the energy operations as the energy operators of quantum systems. We discussed the key component the interaction Hamiltonian, which governs how systems interact with one another. We also examined examples like the dipole interaction Hamiltonian. So understanding Hamiltonians is fundamental to describing and predicting the behavior of quantum systems, whether in quantum computing, quantum sensing, or optical technologies. So thank you for watching, and I look forward to see you in the next lecture as we continue unraveling the mysteries of quantum optics. Until then, stay curious and keep enjoying the quantum world.